You ever ask an AI a question and get a brilliant answer, but you have no idea how it got there? It feels kind of like magic, right? Well, that magic is also a huge problem. And today, we're going to look at a wild new idea for cracking that mystery, an idea that comes straight from the world of quantum physics. All right, let's get into it. So this is the central problem with so much of modern AI. We've built these incredible tools that can write poetry, generate unbelievable images, or predict complex stuff. But if you try to ask it, hey, how did you do that? You get nothing. Just silence. Its brain is a total mystery to us, a black box. So let's put a name to this. This isn't just some academic curiosity. It's actually one of the biggest roadblocks in AI right now. People in the field call it the interpretability problem. And what's so ironic is that the thing that makes these neural networks so powerful is exactly what makes them so mysterious. I'm talking about the millions, sometimes billions of connections all firing at once. That incredible complexity is what lets them learn, but it's also what makes it basically impossible for us to follow their train of thought. Yeah, it's like trying to trace one specific drop of water through the entire ocean. Good luck with Okay, so if the very structure of the AI is the problem, where on earth do you even start to look for a solution? Well, believe it or not, the answer might come from a totally unexpected place: quantum field theory. I know, that sounds super intimidating, but stick with me, because the core idea is actually pretty straightforward. It all boils down to an idea that you probably learned in middle school math: a summary statistic, right? Imagine you're looking at a huge crowd. You can't possibly know every single person's height, but what can you do? You can calculate the average height. That one number, the average, gives you a simple, kind of blurry, but still useful summary of the entire crowd. And you can build on that. You start with the average. That's your first, very basic layer. Then maybe you add another statistic, like the spread. Are most people around the same height, or is there a huge variation? Okay, now the picture is a little sharper. Then you add another one, like skew, to see if the data is lopsided. See where this is going? Each new summary statistic you add is like another layer of detail, bringing the whole picture into clearer focus. And believe it or not, that is the big idea from physics. Quantum field theory basically does the same thing. They just use a much fancier name for it: endpoint correlation functions. But really, it's just their version of our summary statistics. As this quote here explains, each new function, each new layer, helps resolve finer and finer detail, letting them build a complete model of a really complex system piece by piece. So taking this idea from physics, some researchers have built a brand new kind of neural network, and that is the star of the show today. It's called the NCoder. Okay, so what makes the NCoder so special? Well, a normal autoencoder, which is a common type of AI, basically takes some data, squishes it down into a compressed code that it makes up on its own. They call this a latent space. The problem, that space is a total black box. We have no idea what it means. But the NCoder, it's different. It's not allowed to make up its own secret code. Instead, we force it to use a latent space that we've already defined, one made up entirely of those summary statistics we can actually understand. So you can almost think of the whole thing like a little detective story. The first half, the encoder, is the detective. It shows up at a complex scene, say an image, and its job is to ignore all the noise and just write down the key facts in its notebook. These facts are summary statistics. Then it hands the notebook to the second half, the decoder. The decoder is the police sketch artist. It has never seen the original scene. Its only job is to try and recreate it perfectly, using nothing but the detective's note. All right, that's the theory, and it sounds pretty cool, but does it actually work in practice? I mean, can you really build a whole image from just a handful of statistics? Well, let's see. They tested this on the famous MNIST dataset, which is just a huge collection of handwritten numbers. Okay, so first up, here's what the sketch artist, the decoder, drew when it was only given one clue: the average pixel brightness. And while it's pretty much just a blurry mess, right? If you squint, you just might, see the faint outline of a number 7, but yeah, it's not great. But now, check this out. We give the decoder a second layer of clues. This time, we're not just telling it the average brightness, we're telling it how pairs of pixels relate to each other. And just like that, something starts to emerge from the static. You can really start to see the shape of that 7 taking form. And for the final step, we give it the third layer of clues: how groups of 3 pixels relate to one another. And bam! There it is, a perfectly clear, recognizable number 7. And what's so wild is that this image wasn't just copied, it was built from the ground up, using only a statistical description. It's basically an image made of pure math. And the data from the experiment is it's just wild. They had another AI try to guess the number based on these reconstructed images. With just that first blurry image, the AI was right only 3% of the time. Basically just guessing. When they added the second layer of stats, the accuracy jumps to 72%. Not bad. And with all 3 layers of statistics, a perfect 100% score. It proves that all the necessary information to see the 7 is captured in those stats. Okay, this is seriously impressive for a simple black and white number. But, the next logical question is, does this cool trick still work when the images get a lot more complex? And this is where we hit a bit of a wall. For now. On the left, you've got our nice, clean 7. On the right, that's what the encoder produced when trying to reconstruct a picture of a handbag. It's back to being a blurry mess. And the reason is pretty simple. A complex image like a handbag has way more intricate details and relationships. To capture all that, you'd need to go way beyond just those first 3 layers of statistics. So what's the big takeaway here? What does all this mean for the future of AI? And why does getting inside this black box matter so much anyway? Well, it matters because AI isn't just for making cool pictures anymore. We're starting to hand over really high-stakes decisions to these systems. Think about it. Do you want to trust a medical diagnosis if you have no idea how the AI reached it? Or a loan application that gets denied by a system that can't explain its reasoning? And for sure, you want to know why a self-driving car just decided to swerve. If we can't understand the why, we're just taking a leap of faith. And that really brings us to the big final question this research raises. What if this is a glimpse of a totally new way to build AI? Imagine a future where, instead of creating these mysterious all-or-nothing black boxes, we build our AIs layer by layer, out of pieces we can actually point to and understand. A future where AI isn't magic, but a tool we can finally look inside and see exactly how it works.